what I'll ask you to do is evaluate this thing. I haven't explained what it is yet. Some of you probably haven't seen it before. But what you do is you place the correct numbers into the correct boxes, and the way you get that template is from control. CTRL. So control, and then you press that button next to the 1. Put the numbers in, tell us what the answer is, and then it's down to you to figure out what the relationship is between these numbers. Have you got your calculator? Have you put that in as well? What was your answer?
3.
3, okay. So the answer is 3, which means somehow all of these numbers are related. And the big hint there is that the current chapter we're doing is indices and logarithms. So there's a 2, there's a 3, and there's an 8. Obviously it's not 2 times 3 or 2 plus 3.
2 to the power of 2.
Yeah, 2 to the power of 3. So 2 to the power of 3 is 8. And what we've just shown is that a logarithm is just another way of writing an exponential equation, where you take the exponent, 3, and then you place it as the subject. Okay? That's the only difference. We're just rewriting it in another way, but there's advantages to doing this. And we'll get into the advantages in a moment. And below your title, we're going to write down the relationship between those numbers that we had just before. So we have, write them big, 2 to the power of 3 is equal to 8, which obviously is true. And that's the same as, we'll put a double-headed arrow, that's the same as 3 equals this. That 2 there, that 2 sits a little bit below the G, kind of like a subscript, and you put the 8 in brackets. In your book, the brackets won't exist, but it's a good habit to get into. That 8 is related to the log. So 2 to the 3 equals 8 is the same as 3 equals this thing. Now, we should also label what's the same. So the 2 there, that's the base. When we have it in logarithm form, the base comes next to the G. We also have the 3, which is our exponent. And the exponent becomes our subject when we use log form. The last one's the 8. There's many different words that people use to describe 8. Answer, number, argument. I like to just write answer. But if you're familiar with any other forms, then you can write that as well. There's no agreed name. Just like there's no agreed name for the exponent. Some people call it index or power. Okay, below this we're going to write out exactly how we'd say it. So, in quotation marks, the logarithm, log is short for logarithm, so if you hear me say log, I'm referring to logarithm. The logarithm of 8 to base 2 is equal to 3. So I'll underline some key parts. Logarithm of 8, that 8 there is referring to what our answer would be if it was in index form, but we've also got to state the base, and we've also got to state the exponent. So if you want to label this exponent, and when we've got an equation written in log form, basically all that does is it takes the exponent and puts it as the subject of the equation. Okay, now we've got a pair of equations using numbers. Let's write a general form using letters. And the general form will have a to the power of x equals y. And we're saying a, x, and y could really be anything. And that's going to be the same as in log form. It's just about rearranging where those numbers exist. So if I ever forget, I look back to my example. So that 3 should be the exponent, and the exponent here is x. So x equals logarithm. We write the base, and here the base is a, base a. And we write out our answer. So our answer would be y. Once again, I place brackets here. The book doesn't, but it's a good habit. Now there's a few conditions on this. Firstly, so a few key points, if you want to put a star here. A can only take a certain set of numbers. So A takes these elements. All positive real values. Can't be 0. And it can't be negative. In fact, I'll show you why it can't be negative. So here's an example. Negative 2 to the power of x. I think I showed one student the other day. Now if you try to make a table of values, you don't have to copy this down, but it's just to show that it can't work with x and y. Okay, so let's say x is 1, 2, 3, 4, and this is y equals. If I sub in 1 to x, what would be y? So it would be negative 2x to the power of 1, which is just negative 2. Great. So it's just negative 2. Now, if I subbed in 2 to x, in other words, I'm squaring negative 2, what do we get? Positive 4. And then negative 2 to the power of 3? Negative 8. Then positive 16. And what you see is your graph going up and down, up and down, up and down, and it's not a true function anymore. So that's why we can't ever have negative numbers in our base. We can't have 0 either. Now, there's one other thing that you can't have. We use a set difference symbol. Try and remember this from term 1. The set difference symbol also means that we have to exclude the number 1 for the base as well. Now, the reason why we exclude the number 1 for the base, now if we did have the number 1 for the base, then no matter what our power is, 1 to any power is always going to equal to 1. So it's not a true function anymore either. Well, it is a function, but it's just going to be a horizontal line. So that's why we also exclude the value of 1. Okay, that's a condition on A. A condition on Y. Y can only take the elements of the real positive values as well. And once again, I'll show an example of y. Let's say we've got 2 to the power of x. So we've chosen a base, and the base is correct because it's positive and it's not 1 and it's not negative. But we're saying that whatever our answer is, our answer can never be 0 or less. Why is that? Why can't it never be negative? What do you think? Yeah, A can't be negative. What else? If we do this repeated multiplication as many times as we want, what do we get? 2 squared. 2 times 2 is 4. Then double it again. 8, 16. It's never going to be a negative number. If we go the other way by halving, half of 2 is 1. Half it again is a half. Then a quarter. And an 8. It'll approach 0 but never hit 0. So that's why we say that our answer to this exponential equation must never be 0 or negative. So that's the other condition. Okay, this is the general form. Now let's do some examples where we apply logs. Okay. So, before we do that example, let's summarize what we've learned. We'll copy this down. Logarithms help us find the exponent. Logarithms help us find the exponent of an exponential equation which really just means whatever the log equals to, it equals to the exponent. And we'll use this fact to help us figure out a few questions. Okay, take a seat anywhere you want. I'll give you your test in a moment. So e.g., and these questions are asking us to evaluate. Question A, log base 2 of 32. Okay, let's do this question. It's going to turn out to just be a number, but there's two ways to do this. So one way to do this is to figure out what the answer is by first changing it into an exponential equation. So here's what we do. Let log base 2 of 32 equal to our answer. We don't know what our answer is, but let's just call it x. And x is going to give us our answer once we solve for it. So we've got this log equation, and we can change it into an exponential equation just by moving the numbers around. So we've got to identify the base, the index, and our answer. What's the base in this log equation? 2, okay? 2, and the index, x, 2 to the x is 32. And all of a sudden it turns into a form that you recognise. Now the answer to this would be, well, 32 would be the same as 2 to the 5. So 2 to the x is the same as 2 to the 5. And if we equate the indices, we get x is equal to 5. That's one way to do it. So we found out what x is, and at the end we write, therefore, 3 dots, log base of 2, log base 2 of 32 is equal to 5. It's one way to do this. Just let it equal to x, change it into exponential form. Here's another way. So this is question B, and we're going to do the same question, log base 2 of 32. And this time we're going to use the fact that logarithms help us find the exponent, and logarithms help us find the exponent. I'll make that emphasized. In other words, if we have a base of 2, what power must be connected to this base of 2 to make it 32? 2 to the power of what? 2 to the power of 5. That's it. You can go just one step. Well, 2 to what power? 2 to the power of 5 makes 32. Now, if you want to add in an extra step to show where this comes from, that 32 is the same as 2 to the power of 5. And as soon as you've identified the power of that 2 to make you 32, the answer is just equal to 5. In other words, and this is one of the laws you'll learn in a moment when we do log laws, a log and a base cancel each other out if the base of the log and the base of the number is the same. Okay, a few more. Question C, we need to evaluate log base 3 of 81. A couple of ways to do it. I've got my own preferred way, and that's to use the way we did in example B. And the question you should be asking yourself is, 3 to what power makes you 81? 3 to the power of what? 3 times 3 is 9.
3. Oh, I know.
4. 3 to the power of 4 is 81. Okay, and once you've identified what the power of 3 is to make 81, you can cancel out the base of the log and the base of the answer. So the answer is just 4. We'll do one more. Question D. Log base 2 of 1/8. We're going to use a similar method, and that is to change the 1/8 into a base of 2. So it'll be log base 2 of, I can change the 8 into a base of 2, which would be 2 to the power of 3. Okay, but we're not done yet because that 2 there, it's a numerator 2, not a denominator 2. So I flip it to the numerator, log base 2 of 2 to the minus 3. And our answer is just obtained by reading off the exponent. It's -3. Now this tells us that if we double, we need to double backwards. And doubling backwards is the same as halving. If we halve 2 3 times, we get 1/8. Sorry, not 2. If we halve 1, if we start at 1, and we halve 3 times, we get 1, then a half, then a quarter, then an eighth. That gives us our answer of 1/8. Okay. Now there's something I'll add on the board, and it'll be down to you whether you want to copy this down or not. Why logs? It's a question that everyone should always ask from time to time. Why should we learn this? So here's an example of an exponential equation that can't be solved easily. 2 to the x is equal to 6. Turns out that logarithms help us answer this question. Now we could do a bit of guess and check, see what values of x it should fall between, and we know that 2 to the power of 2 is 4, and 2 to the power of 3 is 8. Okay, I'm just looking for numbers that are close to 6. So could you give me an estimate of what x could be? Yeah, somewhere between 2 and 3. Now, we can't know for sure, but a calculator has all these answers to the logs stored inside. So if you did turn this into a log equation, log base 2 of 6 equals x, and you place this inside your calculator, just like what you did before, your answer for x would turn out to be 2.584996, and it keeps on going. Turns out it's not a rational number. So logs help us answer these sorts of questions, and this will actually be the next exercise. Not the current exercise, but the next one. But I'll rub this out for now because we're not up to that. But I hope it gives you a bit of context of why we're doing this. So now we're up to simplifying logarithms. With our indices, we had a set of index laws. We had 5 index laws. There are also 5 log laws that help us simplify logarithms. So we're going to copy down as a title, log laws. So here's the first log law. Law 1. And law 1 is what happens when we are adding together 2 logarithms. Now notice that both of these logarithms have the same base. The only time when you can add logs, add or subtract logs, or even use any log law is when you've got the same base. Now the result of this is the same as log base A of the product of their answers. Now in red, this is optional, only if you want to copy down. But the way this links to index laws is the fact that our first index law says that if we are adding together 2 indices, that implies we must have multiplied the same bases. Our log just goes the other way. If we're multiplying 2 of these numbers, it implies that we've added these 2 indices. Remember, logs tell us what the index is. So really, this is just another way of representing an index. Now we'll do the other log laws. But before that, e.g., just a quick example of how we use this. If we have log base 6 of 4 plus log base 6 of 9, here's our first example that links to law 1. Individually, we can't evaluate it. In other words, we can't find a power of 6 that makes 4. But if we are able to combine it together, log base 6 of 4 times 9, which is 36, then we can evaluate it. What would it be? 2. Why 2? 6 squared. The base to the power of 2 is equal to 36, and the answer would be 2. Okay, that's where log laws help us. Law 2. Law 2 is when we are subtracting two logs from each other. If we have log base a of m and we subtract log base a of n, that will give us log base a of
M over.
Have you done logs before?
No, I was just saying the notes from the book.
I'll tell you notes. Yeah, it actually is. So it is m over n. If we are subtracting two logs, then we divide the answers. So the way this links to log laws, the way this links to index laws is if we are dividing two of the powers that have the same base, then what we would have done is we subtract their indices. So this is how they're related. Quick example of how we use this, e.g. log base 5 of 10, take away log base 5 of 2. Individually, we can't work out their logarithms, but if we combine it together, it will be log base 5 of 10 divided by 2. And now we can evaluate it. The question is, what power of 5 gives you 5? 1. 5 to the power of 1 is 5. Okay, that's law 2. Law 3. This is what happens when you have a log and it's being multiplied by a coefficient. We call that coefficient p. So what you can do to simplify this a bit is you take the p and you raise that m to the power of p. In other words, just taking it and placing it as the power of p. Let's write this down. Log base a of m to the power of p. Once again, this is related to log law. Index laws. A to the power of m to the power of n is the same as a to the power of mn. If we're multiplying two logs, because that p multiplied by a log, you can consider that p acting like a log. If they're being multiplied together, that's the same as one log raised to the power of another log. Okay, now quick example, e.g. if we had 3 times log base 2 of a, then I can get rid of that 3 from the coefficient by moving that 3 inside the brackets. Log base 2 of Have you all just finished writing this? Have you all written down the answer, or are you all still waiting for me to finish? What's the answer? What do we put inside? Take the paraphrase. Okay, now we've got 2 more log laws, but I think we've run out of room on this side, so I'm going to rub out the other side of the board. Next we'll have law 4. Law 4. This is what happens when we have log base a and the number inside has the power of -1. Law 4 is related very closely to law 3. So what happens here is that because we have a power of the number inside, we can use law 3 to bring that power outside as a coefficient. It's just using law 3 backwards. So that -1 gets brought out, and I can write it as the negative of log a of m, log base a of m. Okay, quick example, e.g. log base a of 1/2. I'm looking at that 1/2, and there is actually a negative exponent in there. It's just hidden in a fraction. So we can rewrite this as log base a of 2 to the -1. And then, because I've got that minus 1 there, I can bring it out and make the whole thing negative 4. So this is law 4. Law 5, this is our final one. It's a combination of two parts. If we have log base a of 1 equals to 0, I should say, if you see this kind of thing, log of any base to 1, the answer is always going to be 0. And here's why. If we change this into exponential form, base a to the power of 0, what's that always going to equal to? 1. Anything to the power of 0 is always 1. In other words, if you have log of any base to 1, the answer is always going to be 0. So this is one part. The other part of law 5 is the fact that if you have log of any base to itself, the log of any base to itself is always equal to 1. And the reason is, if you change this into index notation, b to the power of 1 is always b. Okay, 5 log laws. We're going to do some examples with simplifying these log laws. I think I've mentioned already, but this would have been a 2 or 3 week unit in advanced maths. We're going to do all this in one period. Okay, so e.g., simplify. So our expression to simplify is 2 times log base 10 of 3 plus log base 10 of 16. Take away 2 log base 10 of 6 over 5. Okay. Jump into a very hard one to start off. But it's all based on using our log laws. I'm going to write a few extra steps here. It's down to you whether you want to copy it down or not, but this would be the steps that I would always follow. And the steps that I would always follow is I look out for coefficients, and then I find a way of getting rid of them. And the law that I use to get rid of them is law 3. Remember, if we have a coefficient multiplied with a log, I can bring that coefficient inside these brackets. That gets rid of them. Now, the reason why I do this is because these log laws only work when there are no numbers in front. See, all of these logs, there's nothing in front. So I need to get rid of the coefficients first. And I see a pair of these that do have coefficients. So let's work these out. Back down. Okay. Our next line would be log base 10 of 3 to the power of 2. Okay, I bring that coefficient in. I don't need to do anything with the next term, but I copy it down anyway. And lastly, I bring in the 2 into the brackets. Log base 10 of 12 over 10. Okay, I multiply 2 by 6 and 2 by 5.
Wait, can you just backtrack one? What do you do with the 2?
2. See, 2 times 6, 2 times 5.
Don't you put it as a power outside the brackets?
The power, 6 to the power of 2, and 5 to the power of 2.
Yeah.
Yeah. Did anyone else notice that mistake? Yeah. Okay. Please call out if you do. A very common mistake is just not doing the correct operation. So it's 6 to the power of 2 and 5 to the power of 2. So that would be 36 out of 25. Okay, we're almost there. We need to add 2 logs and then subtract a log. So let's do this all together. So now we're going to be using log laws 1 and 2. When we add together logs, we would multiply their numbers together. Log base 10 of 9 times 16. And then that subtraction implies we divide. Divide by 36 out of 25. If you notice, I wrote the 9 times 16 a little bit high because I want to turn this into a fraction because I know my other number is also a fraction as well. So then at the end, it's just about simplifying this fraction inside. Log base 10 of 9 times 16 over 1 multiplied by 25 out of 36. Almost done. Let's simplify. 36, 9 can be found in 36. So 9 times 4 is 36, and 4 and 16 can simplify. So we've only got 4 times 25 that's remaining, which gives log base 10 of 100. We're almost at the end. All that's left is to evaluate this logarithm. The question we ask is, what power of 10 gives us 100? So it's 2. All that monster is just equal to 2. It's down to you to know how to use the log laws effectively. Now we're not done. Don't think you're done, because we've got 4 more examples to do. And the examples are harder. What we just did. Have you got all the log laws copied down? Yeah? Okay. Would have been better if they were left on the board, but no board space. Okay, so here's the next set of examples. And these examples we need to solve. E.g., solve. Question A. And the question is, log base 5 of x equals 3. So the question we're asking, really, is base 5 to the power of 3 is what? Let's rewrite it as an exponential equation. X is our answer, our base is 5, our index is 3. If you change it into a different form, very often it's much easier to recognize. So what is 5 to the power of 3? 125. Right, and that's it. That's what x is. Which means if you sub 125 into x and put this in your calculator will show you 3. Next, question B. Log base 5 of 2x plus 1 equals 2. What you'll find is that when we're solving log equations, very often we turn it back into an exponential equation because it's more familiar to us. So let's turn this into an exponential equation. We start with our base, 5, our power, 2. It's all equal to 2x plus 1. Okay, and this is a very, very easy equation to solve. So we've got 25 is equal to 2x plus 1, minus 1 both sides, and divide by 2. Make sure x is sitting on the left. Okay, 2 more. Example C. Notice that throughout both of these examples, we're always trying to find a way of turning it back into exponential form. So here's our next one. Log base 2 of 2x plus 1, take away log base 2 of x minus 1 is equal to 4. Let's do that. You do that now. Now we've got 2 logs here, and we can't turn separate logs into an exponential equation, which means we've got to find a way of combining these together. Fortunately, we've got a pair of log laws that we can use. One of these log laws. So how do we combine it together? Log base 2 of what?
2x plus 1 over x minus 1.
2x plus 1 over x minus 1. Okay? Eventually it becomes so natural to you that you don't even have to think about your log laws, you know what to write down. And that's all equal to 4. Okay? At this point, we can turn it into an exponential equation because we've got a single log. So we identify our base, which is 2, identify our index, which is 4, and that's all equal to 2x plus 1 over x minus 1. We'll finish the rest up. 2 to the 4 is 16. And I'm going to multiply the denominator on both sides. And that's all equal to 2x plus 1. Expand, 16x. And finish this up. 14x equals 17. X is 17 over 14. Okay, got one more. Here's example D. We need to solve log base 3 of x minus 1 plus log base 3 of x plus 1 is equal to 1. This is our last one. Looks very similar to the previous example. Where instead of a minus, we've got a plus. Sonia, what do you think? What should be our first step?
So you can multiply them together. The x minus 1 and x plus 1.
Okay, and you're using one of the log laws
Yes.
to bring it together. Great. So we've got x minus 1 and x plus 1. At this point, you can choose to put square brackets there if you want, but just remember they're both together with the log. And that's all equal to 1. Okay, now if we've only got a single log, I change it to an exponential equation. 3 to the power of 1 is x minus 1, x plus 1. And now it's just about solving this quadratic equation. What you can do is expand the right-hand side. If you notice that it's difference of perfect squares, you can write down the result. X squared minus 1 is 3. Then 4 is equal to x squared. Then at the end we've got x is equal to plus or minus 2. But we've got to be careful at this point. Can't have a negative. Can't have a negative inside our brackets here. Remember, it was one of the conditions that we had that you copied down. If you see a negative answer, check if it's going to make your answer in these brackets negative. If it is going to make it negative, you get an undefined result. So what you would write down is so any kind of explanation that one of these is undefined. The original equation is undefined for x equals negative 2. You write that down as an explanation, and at the end you write down the actual answer, therefore x is 2. Now I'm going to summarise the hardest bits. Personally, I think it's quite easy to evaluate logs. For example, if I had log base 4 of 16, it's easy for me because all I need to think about is what power of 4 gives you 16, it's 2. The hardest bits are how we simplify. Now you need to be very fluent with simplifying these log expressions because the purpose of simplifying log expressions is to be able to bring all of these logs together into a single logarithms. And that's what's going to help you solve these log equations.